Hello, this is Sarah Dantino.
Jenna Jensen.
And I'm Daniel Walls, and we will be presenting a review of the theorems from Chapter 1 from Stacey Rodman's Introduction to Linear Algebra. These theorems will be an important way to set up a strong foundation for knowledge in future linear algebra studies.
So to start off, we are going to begin with Theorem 1. Theorem 1 says, let V equal the point V1, V2, V3, where V1, V2, and V3 are arbitrary real numbers. Norm of V is given by the formula the square root of V sub 1 squared plus V sub 2 squared plus V sub 3 squared. Our goal is to prove that the points V1, V2, V3, that the norm or magnitude or distance, those are three interchangeable words, is equal to that formula. To start off, we're going to look at a Cartesian coordinate system. Reminder, we are going to be working in 3 space. That means that we can go in the x direction, y direction, and the z directions. So our coordinates are going to have 3 real numbers. To start off with this theorem, we are going to simply plot point V1, V2, and 0. We know that V1, V2, and 0 live in the xy plane because we are not going any direction in z. We are simply at V1, V2. We know that the distance V1 is from the origin to the point x on the x-axis, and the distance for V2 is the distance perpendicular to x up until y. So we know we have the distance V1 and V2. We are going to call the missing distance c. So we have V1, which is the distance of x, and we have V2, which is the distance of y. We know that the distance, the line V2, is perpendicular to the x-axis. With that, we can say that we have a right triangle. What do we know about right triangles? We can use the Pythagorean theorem. So we are going to use the Pythagorean theorem to find the distance of c. We then have V1 squared plus V2 squared equals c squared. From there, we are going to solve for c and take the square root, and we get the square root of V1 squared plus V2 squared as the distance for c. From there, we then plot our full point, V1, V2, V3. We know the distance of c now, and we know the distance of the line going from perpendicular to the xy plane up to point V3 will be the distance V3. The distance from the origin to this point is our magnitude. That is the distance we are trying to find. We know the distance c and we know the distance V3, but we do not know the magnitude. From there, we know that the line with the distance V3 is perpendicular to the xy plane. We know that it runs parallel with z because it is simply in the z direction. We then have another right triangle. So what can we do again? We use the Pythagorean theorem again. We then know that v squared is equal to c squared plus v sub 3 squared. From there, we figured out what c was, so we can plug in c squared. We can plug in what we know for c, and we end up with this result. The magnitude of v is equal to the square root of v1 squared plus v2 squared plus v3 squared. From there, we know that the square root squared cancels out, and we are left with the formula that we needed, v1 squared plus v2 squared plus v3 squared. To look back on that, as a reminder of how we did this, we started out with one right triangle, found the distance of c using the distances of v1 and v2. We then went on and plotted the whole point and had a right triangle again and used our distances of c and v3 to then find the distance of v. We will now move on to Theorem 2.
Theorem 2 states that for any ordered triple v in R3, there exists an ordered triple x such that when x is added to v, the result is the origin. For a given v, such an ordered triple is unique. Geometrically, the vector x can be defined as negative v1, negative v2, and negative v3. We start by knowing that point v plus point x equals the origin, as given from the theorem above. We can break this into the coordinates and see that v1, v2, v3 plus x1, x2, x3 equals 0, 0, 0. Furthermore, we can add the coordinates together and see that v1 plus x1, v2 plus x2, v3 plus x3 equals 0, 0, 0. When we isolate the equation within each coordinate, we see that v1 plus x1 equals 0, v2 plus x2 equals 0, and v3 plus x3 equals 0. In this case, we're going to solve for each x coordinate, and we see that x1 equals negative v1, x2 equals negative v2, and x3 equals negative v3. Therefore, when we combine it back into one point, we see that point x equals negative v1, negative v2, and negative v3. Now, to prove uniqueness, we're going to do a proof by contradiction. Let's say that there exists a point A such that when added to v, we get a unique result for A. So point V plus point A equals the origin, and A is unique. Therefore, similarly to our last step, we see that V1 plus A1, V2 plus A2, V3 plus A3 equals 0, 0, 0. Therefore, following the similar steps, we see that point A is also equal to negative V1, negative V2, and negative V3. However, we said, well, in this case, point A would equal point X, but we said that point A was also going to be unique. So therefore, X is a unique solution. Theorem II, Part 2 states that for any ordered triple V in R3 and W in R3, there exists an ordered triple Y in R3 such that when Y is added to V, the result is W. For any given V and W, such an ordered triple is unique. Geometrically, the vector Y can be defined as W1 minus V1, W2 minus V2, W3 minus V3. From our given theorem, we know that point V plus point Y equals point W. Therefore, we can identify each of the coordinates and see that V1, V2, V3 plus Y1, Y2, Y3 is equal to W1, W2, W3. If you can't tell already, we're going to use a similar process as we did in proving the first part of this theorem. We can combine the coordinates to see that V1 plus Y1, V2 plus Y2, V3 plus Y3 equals W1, W2, and W3. Each coordinates we will break into their own equation. V1 plus Y1 equals W1, V2 plus Y2 equals W2, and V3 plus Y3 equals W3. We will solve for Y within each coordinate, and then combine it back to one point. So therefore, point Y equals W1 minus V1, W2 minus V2, and W3 minus V3. We also need to prove that this point is unique, which we will also do by contradiction. So we need to say that there is a point B such that when V plus B equals W, B will be a unique result within itself. We're going to follow similar steps and add V1 and B1, V2 and B2, V3 and B3 to equal W1, W2, and W3 respectively. We will then solve for each coordinate of B, finding that we're left with B equals W1 minus V1, W2 minus V2, and W3 minus V3. Then we will be left with the fact that Y is equal to B. However, we cannot allow this because we said that both B and Y are unique, so therefore Y is unique. Theorem 3. For any 2 points, V and W in real space, such that V does not equal W, there exists a set of points describing a line passing through both V and W. For all intents and purposes, we will be talking about 3 space. So, we have our points V and W, and they can be anywhere within 3 space, but arbitrarily we will put them as shown right here. Now, to get from V to W, as we established in Theorem 2, there is a unique vector w minus v. Now we have this vector w minus v when we start at v to get to w, and that connects the dots. But we need to move beyond just connecting the dots. We need to describe the line moving through these 2 points. So we can scale w minus v longer, we can scale it shorter, and heck, we can scale it in reverse, and in reverse to another distance. And we can scale it infinitely as many times such that we have created this line that passes through points v and w. So let's build this line. We start at the point v, v1, v2, and v3, and we travel in the w minus v direction with varying magnitudes. We'll call those various magnitudes t, and those t are in R, being real numbers. So we come up with this formula which describes the set of points that create the line. S equals v, v1, v2, v3, plus t times w minus v, w1 minus v1, w2 minus v2, w3 minus v3, such that t is a real number. So we've created the line. Now we need to prove that it passes through both of our points v and w. We have our formula to describe the set of points that will create this line. To prove that the line passes through point v, we're going to choose our scalar t to be 0. So then, at this point, we would have that v1, v2, v3 plus 0 times w1 minus v1, w2 minus v2, w3 minus v3. Each of the coordinates within this point would go away due to multiplying them by 0, so that when we deal with each of the coordinates, we have v1 plus 0, v2 plus 0, and v3 plus 0. When we simplify, we see that we're left with v1, v2, v3, and therefore point v is in the set that we have described. To prove that the line passes through w, we will use t equals 1. We'll describe this point as v1, v2, v3 plus 1 times w1 minus v1, w2 minus v2, w3 minus v3. When we look at each coordinate in particular, we see that we will get, when we multiply 1, v1 plus w1 minus v1, v2 plus w2 minus v2, and v3 plus w3 minus v3. When we simplify each coordinate, we are left with w1, w2, and w3, which is point w. Now proving that point w is described in this set of points that describes our line. We've generated this set of points. We've proven that v and w are in these set of points. So we have a set of points that describes the line passing through points v and w in R3.
Now we are going to be talking about matrices. We may be dealing with different types of matrices, whether that be 3 by 3, 2 by 2, 3 by 4, or even 100 by 100. Matrix C can have any amount of rows and any amount of columns. For all intents and purposes, we are going to be dealing with a 3 by 3 matrix. The goal when given a matrix is to simplify it to the identity matrix. This is especially true when we are given a system of equations. We are allowed to take a system of equations and put it into a matrix. With that matrix, our goal is to get to this matrix right here. The identity matrix looks like this, with a leading one in every column and every row. Ultimately, that is your goal when trying to reduce a matrix. There's a lot we can tell with an identity matrix. We can tell if a set spans, we can tell if we have linearly independence, and many other things can come from knowing if we have an identity matrix. So how can we reduce these matrices? We have 3 different elementary row operations. The first is you can multiply a row by a constant, you can switch 2 rows, or you can add a constant times a row to another row. Before we go on to an example, we are going to talk about an algorithm that we can use to simplify a system of equations. You might be familiar with this from classes before, but we are going to go over this as a little bit of a review. First thing you should always do is to get a leading 1 in the first row. Getting a leading 1 in the first row and in the first column. From there, you use that leading 1 to multiply and subtract from other rows to get zeros in the first column. You have a leading 1 in the first row, you take that leading 1, you multiply by some constant and add it or subtract it from another row to get zeros in those columns. You are going to repeat with the middle row, middle column, and repeat again with the last row and the last column. The example we are going to be working with is the one shown on the screen. Our first goal, remember, is to get a 1 in the first column, first row. So where this negative 1 is, we want a 1. We are going to do that by dividing by negative 1. We end up with 1, -4, and 0 in the first row. From there, we want to knock out the 5 below the 1. We can do that by multiplying the first row by -5 and adding it to the second row. So we have finished our first step of this algorithm. Our next goal is to get a leading 1 where we see this -19. We can do that by simply dividing by -19. We divide the entire second row by -19 and we end up with 0, 1, and 2/19 in this row. From there, our goal is to knock out the -4 and the 2 above and below the 1. We're going to start off by knocking out the 2 below. We know if we multiply by -2 in the second row, we can then add it to the bottom row. We then want to knock out the -4. We can multiply by 4 and add it to the top row. From there, our goal is to get a 1 in the bottom right-hand row column. We can do that by dividing by 2 minus 2/19. The rest is simple. We can multiply the bottom right number 1 times -2/19 and add it to the second row, and -8/19 and add it to the first row to knock out those zeros above that. We are then left with the identity matrix. Remember, this is our ultimate goal when we are trying to reduce matrices. We can do lots of things with this. We can determine different values when dealing with a system of equations. We can determine if a set spans or linearly independence.
Now we will be presenting Theorem 5. Before that, the summary of the theorem is we will use what we know about bases, and we'll notice that there's an interesting relationship between distinct sets of coefficients from each basis that match to the same point. Remember, a basis for R3 is a set that both spans R3 and is linearly independent. We will be generalizing to Rn. So if tau and sigma are two bases for Rn, then the process of taking the list of coefficients needed to describe any point V using the first basis is matched to the list of coefficients to describe the same point using the second basis. And this mapping is a well-defined one-to-one function and onto all sets of possible lists. So we must show this function that maps from one list of coefficients to the other is well-defined, one-to-one, and onto. And the evidence we will use is that both sets of coefficients are linearly independent and span Rn. Now, what's the definition of well-defined? A well-defined is a function where everything in the domain maps to exactly one object in the codomain. Now, we will prove that the mapping from one list of coefficients to the other is well-defined by contradiction. So we will assume that it's not well-defined. If it was not well-defined, there could be one point in the domain that matches to 2 points in the codomain. We know this cannot be possible because sigma is linearly independent, so there should only be one point in sigma that matches to the same point in the domain. And if it's not well defined, there could be a point in the domain that doesn't map to anything. We know this is not possible because sigma spans Rn, therefore there would be a point, which is a list of coefficients that matches to the same point as the list of coefficients in tau. So now we have that it is well defined. Next, one-to-one. A function is one-to-one if there is only one object in the domain that maps to an object in the codomain. So we will assume that it's not one-to-one. If it's not one-to-one, there is two objects in the domain that match to the same object in the codomain. We know this is not possible because tau is linearly independent, so only one of these points would map to one point in sigma. And onto. A function that is onto when everything in the codomain is matched to an object in the domain. We will assume that it's not onto. Therefore, there's an object in the codomain that's not mapped to by a point in the domain. We know this is not possible because sigma spans Rn. Therefore, there would be a list of coefficients in sigma that would map to the list of coefficients in tau. Here's an application. Because we know the mapping of one set of coefficients with respect to one basis is well-defined, one-to-one, and onto another set of coefficients, sometimes it's useful to take that list and transform it into equivalent ones of the other. This is called change of basis. The basic process of change of basis is you take the matrix with vectors of the basis in columns and multiply that by the change of basis matrix. You will get the corresponding point in the other basis. So why is this important? With this theorem and change of bases, we can find other bases for the same span that are the same size. Basically, you can make linear combinations of one basis to create the other. These ideas have implications for sets that are bijections, meaning one-to-one, and isomorphisms. This is something you can look up in your future studies. With that, we will conclude our video of the theorems from Chapter 1, Linear Algebra by Stacey Rodman. Thank you for watching.